Okay, so first, here's our regularly scheduled reminder of what's coming up. I'm in the student view of the course here. It is December 8th. This is essentially our last lesson for the semester, right? We'll be completing section 5.3, which will then complete chapter 5. We have one last discussion board, and then on Thursday, we're going to just do a review, mostly focusing on chapter 5. I think I'm going to try and do a Desmos activity because I think it'll allow us to do the math a little bit easier, and for you guys to get feedback whether or not your responses are right or wrong a little easier than Pear Deck. So we're going to try that, see how that goes. And then next week is finals week. All right, I'll see you on the 15th, right? And actually, I'll see you on the 14th too. We have one last weekly lesson. Haven't looked to see what that is yet. So we'll see you on, I'll actually end up seeing you guys 3 days in a row. I don't know, can you guys handle 3 days in a row, Mr. Mosley? Could be a little tough. You'll see me on Monday, Tuesday, and Wednesday for the day of the final. Whoa, good times. All right, so there's that. Some of you have already submitted the Chapter 5 self-assessment. Those of you who have, thank you for getting started on stuff, trying to get things done. I do want to caution some of you. I don't recall if anyone in this class period has turned in the Chapter 5 self-assessment or not. I just know that I've graded some of them. And the number one error on them is essentially having to do with the stuff that we're going to talk about today. If you've already done it and you learned something today that helps you do it better, you might want to go back and make some adjustments and resubmit. That depends on you, but there is that. All right. So what's that? That's about it. Couple things that have come up. Let me get started. I actually have that in my slides for today. So we'll get our lesson going here. As usual, if you have questions, comments, concerns, put them in the chat, raise your hand, or just unmute your mic and shout at me. All those options work. All right, there we go. Tuesday, December 8th, 2020. We are in section 5.3 about conditional probability and independence. Today, we're focusing on what is independence and what does it allow us to do. But first, again, this is the last day of new content. Thursday's class will be review. All assignments are posted. Today's discussion board is the last new assignment for the semester. And the free response portion of the Chapter 5 self-assessment is a file upload submission. If you're taking pictures of your work you have done by hand and there is more than one page, add your pictures to a Word or Google Doc and upload that file in the submission area. It will only allow you to upload one file. If you've taken pictures of your work and it's more than one page, and it's two separate files that you've uploaded to your computer to then try to upload to the submission area, it will only let you pick one. You cannot do multiple files. So if you have more than one page of pictures of your work, add those to like a Word document, save that file, upload that file that has the pictures in it, right? Again, you can only take one file. Some people were creative who have submitted already, and they realized they could only submit one file, and they just added the other files to their reflection answer, because that is a text entry answer. So if you're really having troubles and you want to do that, I can figure it out. I'll find it. All right. And one last thing here, based on what I've graded so far, I'm actually going to exit out of here. Go back to the course. In this tree diagram discussion board, all right. Some of you guys who have done this decided that there were also tablets at play. I don't know where that came from. As far as I know, this problem has no tablets involved. There are only laptops and desktops, no tablets, and there are 3 states. Some of the answers that have been submitted so far only consider California and Texas, and New York was omitted, and then they had laptops, desktops, and tablets, which is not the case. So if you're trying to get help with this problem and you've looked one up online, please make sure it's referring to this problem and not a different variation of the problem, because it's throwing off your responses. All right. From the distribution center as the starting point of the tree diagram, there should be 3 branches, California, Texas, and New York. Each of those states has 2 branches, one for desktop, one for laptops. Okay. Just wanted to clarify that. I wasn't quite sure where the tablets came from in some people's responses. Okay, so please take that all under consideration as you're working on stuff. Yeah. Get back into this. Are there any questions before I get into the lesson, the actual lesson? Okay, all right, we'll get going. All right, so first, what is independence? All right. So we're going to consider 2 examples of things that we've talked about previously in the course, and that is tossing a fair coin and the pierced ears example it's one of the main examples we've used throughout chapter 5. It's the large physics course at a college with 178 students, male, female, and pierced ears, not pierced ears, and then flipping a fair coin. All right. For our tossing a fair coin example, when tossing a fair coin, the probability of getting a heads first, event A, the probability of getting a tail second, event B, are both 0.5. Okay? You have a 50-50 chance of getting a heads or a tails. The chances of first tossing a head and then getting a tails on the second toss can be given as follows, right? Probability of B given A is equal to the probability of A and B divided by the probability of A. Probability of A and B is 0.5 times 0.5. Probability of A is 0.5. Right, we do all that, we just end up with 0.5 again. Right, the probability of the second toss does not change despite knowing what happened on the first toss. Okay, so the probability of getting tails on the second toss does not change, even though we know what the first toss was. Again, this goes back to, a coin doesn't know, has no knowledge of itself, right? It doesn't know what just happened and doesn't care. In our pierced ears example, all right, the 2 events were A, someone is male, B, that person has pierced ears. We know the following, and these were results from that problem. The probability that the person was male in the class was 90 out of 178. Probability that someone in that class has pierced ears is 103 out of 178. And the probability that a student has pierced ears given that they're male was 19 out of 90. And that was our conditional probability. Knowing that a student is male changes the probability that the student has pierced ears. We can see this because the probability of B given A, or the probability that the student has pierced ears given that they're male, 19 out of 90, which is not equivalent to the probability that someone has pierced ears. Right? The probability of event B changed once we knew what happened in event A, essentially. Right? So because knowing one thing changed the probability of the other thing happening, right? That's essentially what independence is. So now we get the answer based on what we just talked about. When knowledge that one event has happened does not change the likelihood that another event will happen, then the two events are independent. Right? One does not have influence over the other, so they're independent. Right? When something does have influence over the other thing, we call that dependent or not independent. So our definition straight from the textbook about independent events: two events A and B are independent if the occurrence of one event does not change the probability that the other event will happen. In other words, events A and B are independent if probability of A given B is equal to probability of A, and the probability of B given A is equal to the probability of B. Okay? So we have this condition here that we can actually test to confirm if something is independent or not independent. All right? If one of these two equivalences fails, we can automatically say that the event is not independent. Right? So now, if you need a moment to write this definition down, please raise your hand. I do recommend having this in your notes somewhere. All right. So as you guys are possibly finishing writing this down, I want to point something out in the definition. All right. The last statement in here is events A and B are independent if the two conditional probabilities work out the way it's stated here. So this is, if you guys recall from Math 3, this is an if-then statement. It's a conditional statement. But it's an if-then statement that has an and condition. So both of these things must be true for the conclusion to be true, right? Because this is essentially saying if probability of A B equals probability of A, and probability of B given A equals probability of B, then my pen's being all crazy today. Events A and B are independent. Yes, Caesar. Caesar, did you have a question, or was that an accident?
No, it was an accident. My bad.
Okay, no worries. All right. So again, when you're checking for independence, it's possible that the probability of A given B equals probability of A. You still need to check the other condition, which is the probability of B given A is equal to probability of B. Both must be true to conclude independence. If either of them fails, then we do not have independent events. Right? So just because one of those things works out doesn't mean you get to move on and say it's independent. You must check the other one to be sure. All right. Does that make sense, guys? That's what happens when you have that AND connector. It means both things must happen. Just like when we have an AND connector between two events, in like a Venn diagram and that kind of stuff, to be part of an AND statement, both must happen. Okay. All right. Move on. So now let's look at an example. Determining independence. We have 452 high school students who completed a survey or are randomly selected. The survey was trying to determine if there's a relationship between gender and relative finger length. All right. The two-way table below shows the gender of each student and which finger was longer on their left hand, index finger, or ring finger. This is our data. We want to know, are the events female and has a longer ring finger? Are they independent? So let's just have female be event A, has a longer ring finger, be event B, right? And so we need to check both of those statements from our definition. We need to check probability of A given B. Is that equal to probability of A? And we need to check probability of B given A. Is that equal to probability of B? Okay. And this little question mark above the equal sign, that's a way of saying that I'm not yet saying these are equivalent. I'm wondering if they are, right? So let's do the math, right? So we have a few things that we need to set up. Change the color here. Let's go. So probability of A, probability of B, those are going to be a little easier and more straightforward to come across, right? Probability of someone being a female, right? We have 212 females out of 452. And the probability of has a longer ring finger, right? This one here. We have 234 out of 452. All right. So those ones are easier to kind of see. Then Let's see what our other probabilities are. A given B. Right, this is the equivalent to the probability of A and B divided by the probability of B. A and B, so female and has a longer ring finger, 82. Probability of B, this craziness over here, 234 over 452. I'm sorry, I'm messing up the stuff. Give me a second. Sorry, this is going to be 82 out of 452. So then the probability of B is 234 out of 452, which leaves us with 82 out of 234. All right. So let's check to see, is the probability of A given B equal to the probability of A? And that's the first thing to check. So 212 divided by 452, right? That gives us 0.469. Right? 82 divided by 234, this is equal to 0.350. Right? So we don't have to go any farther. Right? The first condition we tested failed. Probability of A given B, the probability that the student is, the person is female, given that they have a longer ring finger, is not equivalent to the probability that a student is female, meaning knowing one has an influence on the other. So since probability of A given B is not equal to the probability of A, the events are not independent. All right. And so that's how we can go about determining independence. In this case, we didn't have to go on and test the second condition because the first one that we tested failed. What questions do you have? What can I clarify? Does anyone need another moment to write down anything from this example? All right, so we also get another rule, the multiplication rule for independent events. When events A and B are independent, right, P of B given A is equal to P of B. So the general multiplication rule can be simplified, right? This first part, probability of A and B, is equal to, clicking the wrong colors. Right? This first part, probability of A and B, equal to probability of A times probability of B given A. This is the general multiplication rule, right? Start this thing. All right, sorry, just not going to use that for now. All right, so again, this first part here, that's the general multiplication rule. Since probability of B given A is equal to the probability of B, we can substitute it in the rule, right? So when events are independent, if I want to know the probability of A and B happening, I can just multiply their two probabilities, probability of A times probability of B, right? Because knowing one does not change the other, right? So that gives me a slightly easier process if I know the events are independent, which in some cases you will just be told these events are independent, or assume the events are independent, something to that effect, right? And then you can use this rule. This adjustment to the rule only works for independent events. So if you do not know if the events are independent, you just need to use the regular general multiplication rule. Okay. So, and then here's our definition straight from the book. If A and B are independent events, probability that A and B both occur is formula we just discussed. Probability of A intersection B is equivalent to the probability of A times the probability of B. Okay. So, please raise your hand if you need a moment to write down this definition and the rule. Right. So now let's use what we just talked about. In baseball, a perfect game is when a pitcher doesn't allow any hitters to reach base in all 9 innings. Historically, pitchers throw a perfect inning, an inning where no hitters reach base, about 40% of the time. So to throw a perfect game, a pitcher needs to have 9 perfect innings in a row. Okay. What is the probability that a pitcher throws 9 perfect innings in a row, assuming the pitcher's performance in an inning is independent of his performance in other innings? All right. So we have this 40% probability, right, which we can rewrite as, why is this being shaky today? 0.4. Right? So we have a 0.4 probability of throwing a perfect inning. We have a 0.6 probability of not throwing a perfect inning. All right? Probability the pitcher throws 9 perfect innings in a row. Right? So we want the probability of essentially give me a second, guys. All right. Sorry, this is just going to work a little better now. Hopefully. All right. So essentially, we're looking for the probability that we have 9 perfect innings in a row. Which is equivalent to the probability of inning 1, perfect, and inning 2, and inning 3, so on through inning 9. Since these are independent events, this, using our multiplication rule for independent events, is equivalent to the probability of inning 1 being perfect times probability of inning 2, so on through the probability of inning 9 being perfect. These all have the same probability of 0.4. Right? And this will happen 9 times, which is equal to 0.4 to the 9th, which is then a teeny tiny number. So this is equal to 0.000262, approximately. All right. So chances aren't good. Right? So now, it's teeny tiny probability. Yeah. So again, this kind of gives you the reason why we don't see a ton of perfect games, right? And again, this is assuming that they're independent events. One thing doesn't have any effect on the next. One inning has no effect on the next inning. But we end up with a 0.02% probability. Not good, right? Any questions on this problem? All right, so then look at a secondary example here. All right, the first trimester screen is a non-invasive test given during the first trimester of pregnancy to determine if there are specific chromosomal or abnormalities in the fetus. According to a study published in the New England Journal of Medicine in November 2005, approximately 5% of normal pregnancies will receive a positive result. If 100 women with normal pregnancies are tested with the first trimester screen, what is the probability that at least one woman will receive a positive result? All right. So this is a more kind of interesting, involved example here. And I will show you why. So in this example, we have a 5% chance for positive test results. All right. All right, this is 0.05 as a probability. And we want to know what is the probability of at least 1 out of 100 being positive. So the issue with this is the at least. In this case, the probability of at least 1 is the probability of 1 out of 100 being positive, plus the probability of 2 out of 100 being positive, plus the probability of 3 out of 100 being positive. We'd have to essentially do 100 probabilities if we wanted to calculate this straightforward. It's too much work. It's too many things to do. So what we do is we use the complement, because that's going to be easier to calculate. All right, the complement, or the kind of, let's think of it maybe as the opposite of at least 1 out of 100 positive. If I have less than 1 out of 100 positive, that means I got no positive results. All right, so this is equal to 1 minus the probability of no positive results. One second, right? Okay. Do you guys understand how I made that jump? It's not always going to be like apparent when to use the complement of some scenario. In this case, when you start to think about how to find the probability and you start realizing there's so many things to calculate, consider using the complement, right? This is going to be an easier calculation. So here's what we end up with. We have the probability of getting a single negative test is equal to 1 minus 0.05 or 0.95, right? We have a 95% chance when we test a single person of getting a negative test. All right. So essentially, we want to know what's the probability of getting 100 negative results. All right. That's the probability of getting first test negative, right? And second negative, all the way through to 100th being negative. Which then starts to break down as the baseball example, where we use our multiplication rule for independent events. This is an independent thing. One test result has no influence on the second test result, right? The results are for different people, right? Knowing one has no effect on the other. So these are independent events. So we have the first negative times second negative, all the way through again to probability of the 100th negative. which we get 0.95, right, to the 100th power. Which is, because I did this earlier, 0.0059. Right, so this is the probability of getting no positive results out of 100 consecutive tests. Based on what we need up here, the thing we're actually looking for is going to be 1 minus this result. Okay. Which is equal to 0.9941. All right. So there's over a 99% chance of getting at least one positive result out of 100. Okay. So this is our solution for the day. Okay. And again, we use the complement in this case because the complement is something that's more easy to use. If I wanted to straight out calculate this, we could kind of use a tree diagram, but it's going to have a lot of levels. And we would need to figure out, essentially to have probability of getting 1 out of 100 positive, like just 1, right? There's like 100 ways for that to happen. It could be the first test, could be the second test, could be the third test. And we would have to calculate each of those different possibilities happening. So just to find out the probability of just 1 out of 100 being positive would be like 100 calculations. Add those all up. Then, okay, now how many ways can I get 2 positive tests out of 100? And 3 positive tests, which is why this would take forever. But if I use the complement where I just have to consider a single situation of, well, I could have no positive tests. That's the complement of my situation here. That clears it all up. Now I can use this one thing to do my calculations rather than doing, thousands of calculations. Okay. What can they clarify? Then we need another moment to look at this work, and I'll add this work into the PowerPoint slide, so it'll be part of the notes for sure. So don't worry about that. Okay. So something I need to make clear. Mutually exclusive is not the same as independent. Right? I saw some students who did already turn in their Chapter 5 self-assessment who were confusing these two things. This is a very common mistake. 2 events can be mutually exclusive and be not independent. Right? These are not the same things. They're not the same concepts. Right? 2 mutually exclusive events can never be independent. That's straight up. Because if one event happens, the other event is guaranteed not to happen. Right? That means the one thing is definitely having an influence over the other thing. If I know the one, I already get to know something about the other event. That means they're not independent. So knowing one event has occurred changes the likelihood of the other event. Right? Consider the 2 events. A, person is male. B, person is pregnant. These events are mutually exclusive. Person can't be both male and pregnant. However, if we know the person is male, chance of them being pregnant is 0. Right? We also get that probability of B given A is not equivalent to probability of B, so the events are not independent. All right, so these are completely separate things. They could be related, right? But they're not the same. So because things are mutually exclusive or disjoint, because they can't be together, essentially means they're not independent. Okay. Is there anything I can clarify about this? This is a very common mistake that students make. Does anyone need a moment to write anything down from this screen? And that's it. That concludes Chapter 5 about probability. These are the 3 sections of Chapter 5. We had 5.1, randomness, probability, and simulation. 5.2 is probability rules, and 5.3 is conditional probability and independence. And that's all of Chapter 5. So, lastly, in this week's module, right, we have our last discussion board, conditional probability and independence. There are 2 questions. Question 1 has several parts. All right, and essentially, you need to determine if the events are independent. All right, some of it you could logically reason out as being dependent or independent. Others, you're going to need to show the math, right? Or at least explain the math. Please don't forget about question number 2. This one has to do with actually calculating using the multiplication rule for independent events. So this is an opportunity to practice using that. Okay. Along with this, if you look in the live class for resources, I do have 3 other events or 3 other examples from the textbook, little short videos, right? How to check for independence, how to work with independence and multiplication rule, and another example of the at least one type of example where we're using the complement. So if you'd like to see other examples, those are available right here. And there is an AP Daily video that goes along with this lesson. Okay. Again, this is how to determine if 2 events are independent and how to calculate probabilities for independent events. So we do have some extra resources for today's lesson if you like. That's all that I have for you guys today. Is there any questions, comments, concerns, anything else I can support you with? Otherwise, you guys are free to enjoy the rest of your Tuesday, and I will see you on Thursday for the review.